September 14th, 1945. Aberdeen Proving Ground, Maryland. Dr. William Gruber stood beside a Sherman tank that looked like nothing the US Army had ever fielded. 10 inches of what appeared to be solidified tar and gravel encased the turret. Steel cables held strange panels against the hull, panels that weighed 8 tons combined. The assembled officers exchanged skeptical glances. Some suppressed smiles. The material looked absurd, like someone had tried to armour a tank with road construction materials, which was exactly what had happened. The German Panzerfaust 100 in the firing pit had penetrated every armour type the Army had tested since Normandy. Steel plates, sandbags stacked 4 layers deep, concrete trowelled by desperate crews, track links welded frantically to hulls by men who knew they were driving coffins. All of it had failed. Gruber checked his clipboard one final time. The mixture was designated HCR2, 80% quartz gravel, 15% asphalt, 5% wood flour. Washington called it plastic armour. The tankers who'd died in France would have called it something else. They would have called it hope. "Fire when ready," Gruber said. The rocket screamed toward the tank. What happened next would change armoured warfare forever. Stakes establishment. To understand what Gruber witnessed that morning, you must first understand what American tankers faced in Normandy. By June 1944, the M4 Sherman had been the backbone of Allied armour for 2 years. It was reliable. The Ford GAA V8 engine rarely failed. It was fast. 26 miles per hour on roads. It was available in staggering numbers. Over 49,000 would roll off American production lines by war's end. 11 different manufacturers contributed to this flood of armour. Chrysler Defence Arsenal alone built nearly 18,000. Against this tide, Germany produced only 347 Tiger I tanks. The mathematics seemed overwhelmingly favourable. And yet, the Sherman was a death trap. A British analysis of Sherman casualties between D-Day and July 10, 1944, revealed devastating statistics. 60% of tank losses resulted from a single shot. 2/3 of all penetrating hits caused the tank to catch fire. American tankers called their vehicle the Ronson. Like the lighter, it lit first time, every time. German crews called it the Tommy Cooker. Polish tankers called it the burning grave. The fundamental problem was simple mathematics. The Sherman's frontal armour measured 50 mm thick. The German 80mm gun could penetrate 120 mm at 1,000 metres. The Panther's 75mm gun could punch through 124 in at the same range. American crews faced enemies that could destroy them from distances at which their own guns were useless. But the horror didn't end with enemy tanks. By September 1944, a new threat had emerged from the rubble of Norman villages. A threat that cost less than $10 to manufacture. A threat that any conscript could carry. A threat called the Panzerfaust. Section 1. The Armour Fist. The Panzerfaust was born of German desperation. By 1943, German industry was buckling under the strain of a 2-front war. They could not produce enough tanks to match Allied numbers. Every Tiger required 300,000 man-hours to build. Every Panther needed 150,000. Even the humble Panzer IV consumed resources Germany could not spare. The question became urgent. How could Germany counter Allied armour without building more tanks? The solution emerged from a simple insight. They would make every German soldier a tank killer. Hugo Schneider Aktiengesellschaft Metallwarenfabrik, known as HASAG, began development in summer 1942. The company had experience with ammunition and small arms production. Now they turned attention to anti-tank weapons light enough for a single infantryman to carry. simple enough for minimally trained conscripts to operate, cheap enough to produce in the millions. What they created was brutally elegant in its simplicity, a hollow metal tube, essentially a pipe with a trigger mechanism, a shaped charge warhead mounted on a wooden shaft. A small propellant charge of black powder, total weight under 5 pounds, effective range 30 meters for the initial model, penetration capability 200 millimeters of hardened armor steel, more than enough to destroy any tank in existence. The physics of the shaped charge made this possible. When ordinary explosives detonate against armor, most energy dissipates in all directions, but a shaped charge focuses that energy with devastating precision. A copper liner inside the warhead, conical in shape, collapses inward when the explosive detonates. The immense pressure transforms the copper into a superplastic jet. This jet travels at 8,000 meters per second, faster than any bullet. It punches through armor that would stop any conventional projectile. The penetration depth is roughly 6 times the diameter of the warhead. A 150mm warhead could theoretically penetrate 900 mm of steel under ideal conditions. No tank could survive such penetration. No amount of conventional armor could stop it. Hitler himself renamed the weapon. Engineers had called it Faustpatrone, fist cartridge. Hitler preferred Panzerfaust, armor fist. The name captured German hopes perfectly. The weapon entered mass production in August 1943 under direct orders from the Führer. Initial production stood at 40,000 units per month. By the end of 1943, production had doubled. By mid-1944, it had quadrupled again. By war's end, German factories were producing 1.5 million Panzerfausts monthly. The stockpile in November 1944 exceeded 1,676,000 weapons ready for use. Consider the economics. A Tiger tank cost 250,000 Reichsmarks and took months to build. A Panzerfaust cost approximately 25 Reichsmarks and could be assembled in minutes. For the price of one Tiger, Germany could produce 10,000 Panzerfausts. Which represented the greater threat to American armor? The mathematics of armored warfare had fundamentally changed. Section 2. The Hedgerow Nightmare. The bocage country of Normandy was a Panzerfaust paradise. The terrain could not have been better designed for ambush warfare. Dense hedgerows, earthen berms topped with thick vegetation, bordered every field. Some dated back to Roman times. They limited visibility to yards rather than hundreds of meters. Sunken lanes, carved by centuries of cart traffic, created natural ambush positions. The roads wound between hedgerows in unpredictable patterns. A tank advancing down one of these lanes was essentially blind. A German soldier could hide within arm's reach of the road and wait. He could hear the Sherman's engine long before he saw it. He could let the tank pass and fire into thinner side armor. Or he could wait until it stopped to negotiate an obstacle and fire point blank into the engine deck. At 30 meters, the early Panzerfaust's effective range, he could hardly miss. And he didn't need to miss. He needed to hit once. The statistics told the story of a weapon finding its perfect battlefield. In September 1944, approximately 4% of US tank losses came from Panzerfaust and Panzerschreck attacks. This seemed manageable. But the numbers climbed relentlessly. By October, 5%. By November, 5%. By March 1945, during the push into Germany, 25 to 35%. In the final months, shaped charge weapons caused nearly a third of all tank casualties, but the percentages told only part of the story. Infantry anti-tank rockets inflicted 13% of tank losses, but caused 21% of crew casualties. The shaped charge weapons were disproportionately lethal to the men inside. Why? Because of what happened when the jet penetrated. The jet temperature exceeded 1,000 degrees Celsius. When it breached the hull, it didn't simply make a hole. It sprayed molten copper and steel throughout the crew compartment. The superheated metal ignited everything flammable. Ammunition stored in hull racks exploded. Fuel lines ruptured and burned. Hydraulic fluid became an accelerant. The interior became an inferno in seconds. Crews had moments, sometimes fractions of seconds, to escape. Many didn't escape. Those who did often suffered burns covering most of their bodies. The psychological impact exceeded statistical losses. Tank crews began refusing to advance without infantry support, but infantry refused to advance without tank support. Operations slowed as units became paralyzed by mutual fear. A single German teenager with 3 weeks of training and a Panzerfaust could stop an entire armoured column. He might die in the attempt. But so would 5 American tankers. The exchange ratio from Germany's perspective was acceptable. Commanders at all levels reported the same phenomenon. Crews were thoroughly impressed by any protection, even ineffective protection. The morale value of any defence exceeded its physical value. Men facing death will grasp at any hope, however illusory. American ingenuity responded to the Panzerfaust with characteristic desperation. Section 3. The desperate improvisations. The first field modifications appeared within weeks of the Normandy landings. Crews didn't wait for official guidance. They couldn't afford to wait. Men were dying every day, and the army wasn't providing solutions. So they created their own. Spare track links became the first improvised armour. Every tank carried spare links for field repairs. Supply depots had thousands more. Crews welded them to hulls and turrets, creating a bristling coat of steel segments. The logic seemed sound. Track links were steel. Steel stopped bullets. Maybe track links could stop Panzerfausts. The reality was more complex and ultimately disappointing. Track links were not armour-grade steel. They were designed to flex and grip, not to resist high-velocity penetration. The metallurgy was optimized for durability against abrasion, not against shape-charged jets. Tests revealed an even worse problem. Soft track steel could actually normalize incoming armour-piercing rounds. A round striking the Sherman's sloped glacis at an angle might ricochet or deflect, but a round striking a track link welded to the glacis would be turned perpendicular. The track link would guide the round directly into the hull. The very armour intended to protect could make penetration easier. Against shaped charges, track links provided minimal benefit. The copper jet punched through them almost as easily as through air. The standoff they created might actually help the jet form more completely, but crews kept adding them anyway. The psychological value outweighed the physical limitations. A tank covered in track links looked armoured. It looked protected. The crew felt safer, even if they weren't. Sandbags became ubiquitous as the fighting continued. Up to 170 sandbags covered a single tank, 2 to 4 layers deep on the front plate, 2 layers deep on hull and turret sides. Metal frameworks had to be fabricated to hold the bags in place. Without frameworks, bags would slide off during movement. The additional weight reached 3 tons. General George S. Patton was furious when he saw his tanks festooned with sandbags. These weren't the lean, fast machines he'd trained to fight. They were slow, overburdened, and, he suspected, no better protected. He ordered systematic tests at the 1st Armoured Group. The results confirmed his suspicions. A Panzerfaust 60 was fired at sandbagged Sherman tanks from various angles and ranges. Against the side armour, full penetration, no noticeable degradation of the shape-charged jet. Against the glacis plate, The first round blew away the sandbags completely. Subsequent rounds penetrated as if the sandbags had never existed. An observer reported to Washington, "These tests are far from conclusive, and the psychological value of the sandbags is the greatest value actually derived." Another observer visiting units in March 1945 agreed, "If the bags did nothing more, they were certainly a morale factor as the crews were thoroughly impressed with them." Some officers suspected sandbags made things worse rather than better. A shape-charged jet requires specific standoff distance to form properly. The copper liner needs space to collapse into a coherent stream. Too little standoff, and the jet never fully forms. Too much standoff, and the jet disperses before impact. The sandbags might have held Panzerfaust warheads at nearly optimal distance from the armour. By detonating the warhead at perfect standoff, they could have increased penetration rather than decreasing it. The data was inconclusive, but the possibility haunted commanders who approved sandbag modifications. The physical problems were undeniable regardless of shaped charge effects. The weight-stress suspensions designed for 30-ton vehicles now carrying 33 tons. Final drives wore out faster. Transmissions failed prematurely from the concentrated front-end load. Engines overheated as they struggled to move the additional mass. Speed dropped significantly. The Sherman's top speed fell from 26 mph to barely 20 on roads. Cross-country performance degraded even more. The fundamental purpose of the Sherman, mobility, was sacrificed for what might be an illusion of protection. Patton banned sandbags in the Third Army. His reasoning was sound. The tanks slowed down, broke down more often, and the sandbags didn't actually work against the primary threat. But he offered no alternative. Crews in other armies continued piling sandbags higher. Concrete became the next improvisation, as sandbag limitations became apparent. The 12th Armoured Division added concrete slabs containing internal reinforcement bars to hull fronts and sides of several tanks. Crews mixed concrete in field kitchens, the same kitchens that made their coffee and heated their rations. They troweled the mixture onto turrets like medieval masons building castle walls. Some applications reached 6 inches thick. The results were marginally better than sandbags, but still fundamentally inadequate. Concrete cracked and spalled when struck by any significant impact. The fragments became secondary projectiles inside the tank, dangerous shrapnel created by supposed protection. The weight problems were even worse than sandbags. Concrete is heavy, and 6 inches of it adds thousands of pounds. One famous photograph from March 1945 shows soldiers examining a Panzerfaust hit on a sandbagged Sherman. The warhead had blown away the sandbags, penetrated the hull, and killed the entire crew. The sandbags had done nothing to save them, but sandbags kept appearing on tanks until the very last day of the war. Section 4. Patton's steel solution. If sandbags and concrete couldn't work, what could? The answer seemed obvious once someone asked the right question. Patton's ordnance officers had been studying the problem for months. Their conclusion was straightforward. More armour, real armour. Steel plates cut from destroyed tanks and welded to operational vehicles. In February 1945, after the Battle of the Bulge, Patton authorised systematic up-armouring. The source material was grimly abundant. The Ardennes battlefield was littered with destroyed tanks, American Shermans, German Panthers. The hulls were beyond repair, but armour plates remained intact. Ordnance teams cut frontal glacis plates from wrecks and transported them to field workshops. A Panther's frontal plate measured 80 mm thick. Welded to a Sherman's existing 50 mm glacis, it created protection exceeding anything designers had envisioned. 3 Belgian factories near Bastogne handled the volume. The tanks of 3 armoured divisions received modifications. An average of 36 tanks per division were upgraded. Turrets received additional plates welded to the cheeks. Differential housings were reinforced. The results were encouraging. Modified tanks survived hits that destroyed standard Shermans. German gunners reported confusion when rounds failed to penetrate. General Creighton Abrams commanded one of these up-armoured M4A3E8s. His tank, Thunderbolt 7, survived engagements that would have killed him in a standard Sherman. Patton's program proved protection worked, but it was improvisation, not engineering. It couldn't be scaled or standardized. The Army needed a systematic solution. That solution was already being developed at Aberdeen. Section 5. The Flint Coater Answer. While tankers improvised in the field with whatever materials they could find, American engineers pursued a different approach entirely. In August 1943, more than a year before the Normandy invasion, U.S. Army Ordnance began systematic investigation of protection against shaped-charge weapons. The physics were already understood. A shaped-charged jet required a specific standoff distance to form properly. The copper liner needed time and space to collapse into a coherent stream. Detonate the warhead too early, and the liner never fully forms a jet. Detonate it too late, and the jet disperses before reaching maximum velocity. Disrupt the jet's formation through any means, and penetration failed. The question was, what material could achieve this disruption without adding impossible weight? Steel could stop shaped charges, but only through massive thickness. Defeating the largest Panzerfaust with steel alone would require adding 8 to 12 tons to a Sherman. This would overtax the suspension, designed for 30 tons. It would destroy the transmission within hundreds of miles. It would reduce the tank to a crawl, negating its main tactical advantage. There had to be another way. By October 1943, researchers found an answer that seemed absurd at first hearing. Plastic. Not the synthetic polymers we know today, but a mixture of hard aggregate suspended in bitumen, similar to the asphalt used for road construction. The concept originated in Britain. In 1940, Edward Terrell of the Admiralty faced a desperate problem. German aircraft were strafing British merchant ships with machine guns. A single strafing run could kill the bridge crew and leave the ship helpless. But armour heavy enough to stop machine gun bullets would make ships top-heavy and unstable. Terrell's solution was elegant. He developed plastic armour. Small, evenly sized aggregate suspended in a bitumen matrix. The armour was applied 2 inches thick over vulnerable areas. It worked because the hard particles deflected bullets. Projectiles lost energy ricocheting between aggregate particles. They lodged in the bitumen matrix, unable to penetrate the steel beneath. The armour weighed far less than equivalent steel plate. Ships could carry it without stability problems. Thousands of British merchant sailors owed their lives to this strange tar and gravel coating. American engineers recognized potential for shaped charge defense. If hard particles could disrupt bullets, perhaps they could disrupt shaped charged jets. The physics were different, but the principle was similar. Scatter the incoming threat, disperse its energy, prevent coherent penetration. The Flint Coat Company was contracted to develop tank armour. Flint Coat manufactured roofing materials and asphalt products. They had decades of experience with bitumen formulations. They understood how to create mixtures with specific properties. They could produce material in industrial quantities. Testing revealed 2 promising formulations. HCR1 contained 50% aluminum filings, 40% asphalt or pitch, and 10% wood flour. The aluminum provided hardness and heat resistance. The asphalt provided binding and energy absorption. The wood flour prevented cracking under shock. HCR2 contained 80% quartz gravel, 5% wood flour, and 15% asphalt or pitch. The quartz provided extreme hardness, harder than most metals. Less aluminum meant lower cost and easier production. The formulation could be manufactured from materials available anywhere. HCR2 proved superior in testing. The quartz gravel disrupted shape-charged jets through multiple mechanisms. Hard particles shattered as the jet struck them, creating secondary fragments. These fragments interacted with the jet, dispersing it laterally. The bitumen matrix absorbed energy through deformation. As the jet passed through, the tar yielded and flowed. This deformation absorbed kinetic energy and created lateral forces. The wood flour maintained structural integrity. Without it, the armour cracked and spalled under shock. With it, the armour held together even after multiple impacts. 10 inches of HCR2 could defeat a Panzerfaust 100, the most powerful model in German service. This was protection that sandbags could never provide. This was protection that welded steel plates could not match. The jet that punched through inches of hardened steel dissipated harmlessly in gravel and tar. Better yet, the material weighed less than equivalent steel armour. 8 tons of HCR2 provided more shaped charge protection than 12 tons of steel. It could be mass-produced from common materials available anywhere: quartz gravel, asphalt, wood flour. Every road construction company in America had these materials. The solution was ready, but time was running out. Section 6. The Aberdeen tests back to September 1945. The European war had ended 4 months earlier, with Germany's unconditional surrender. Japan had surrendered just weeks before, after atomic bombs destroyed Hiroshima and Nagasaki. But at Aberdeen Proving Ground, the weapons tests continued. The war might have ended, but the knowledge was still needed. American planners had spent months preparing for Operation Downfall, the invasion of the Japanese home islands. This operation would have required tens of thousands of armoured vehicles. Japanese defensive positions featured extensive fortifications and anti-tank weapons. The Type 4 70-8 rocket launcher, Japan's answer to the Panzerfaust, threatened to inflict the same devastating casualties that German weapons had caused in Europe. Intelligence estimated that Japanese factories were producing thousands of these weapons monthly. Every beach, every ridgeline, every urban intersection would have been defended by soldiers equipped with shaped charge weapons. American planners projected catastrophic tank losses. They wanted protection ready before the landings scheduled for November 1945. The atomic bombs made the invasion unnecessary, but the research continued because the principles mattered beyond any single war. Shaped charge weapons weren't going away. The next conflict would feature them in even greater numbers. American tankers needed protection that worked. Dr. Gruber's team had assembled a comprehensive armour kit using HCR2 plastic panels. The kit was designed by the Flintcoat Company, specifically for the M4 Sherman series. Each armour panel consisted of 10-inch thick HCR2 faced with 1-inch aluminum plate. The aluminum provided a hard outer surface that would activate shaped charge fuses properly. Without this outer plate, some warheads might penetrate the soft HCR2 without detonating. The HCR2 itself provided the protective depth, 10 inches of jet-disrupting material. Half-inch steel cables attached to brackets welded to the tank held the panels in place. The cable attachment system was designed for field replacement. If a panel was damaged, crews could cut the cables and attach a fresh panel. The cables could also be cut in emergency, allowing crews to jettison armour if the tank became stuck. The panels covered the sponsons, the hull sides above the tracks where ammunition had traditionally been stored. More panels wrapped around the turret, protecting the crew compartment from all angles. total additional weight, approximately 8 tons. This represented a 25% increase in the Sherman's combat weight. Significant, but far less than the 40% increase that equivalent steel protection would have required. More importantly, the Sherman could still move. The suspension could handle 8 tons of additional weight. The engine could manage. The transmission would survive. The tank retained its mobility, degraded but functional. With steel armor providing equivalent protection, the tank would have been nearly immobile. This was the key advantage of HCR-2. It provided protection without crippling the vehicle. The Panzerfaust 100 waited in the firing pit. This was the deadliest infantry anti-tank weapon of the entire war. Its warhead weighed 3.5 pounds, more than twice the weight of early Panzerfaust warheads. Its effective range was 100 meters, more than 3 times the original Panzerfaust 30. Its penetration capability exceeded 200 milliton of rolled homogeneous armor. No improvised field armor had ever stopped it. Sandbags failed, concrete failed, track links failed. Even the jumbo Sherman's massive steel armor was vulnerable to the Panzerfaust 100 at certain angles. This was the ultimate test. If HCR-2 could stop the Panzerfaust 100, it could stop anything in the German or Japanese infantry. The rocket fired with its characteristic whoosh. The warhead streaked across the proving ground, trailing smoke. It struck the turret at an angle representing a typical combat hit. The shaped charge detonated. The copper liner collapsed inward under enormous pressure. The superplastic jet formed, accelerating to 8,000 meters per second, and the HCR-2 absorbed it. Quartz particles shattered as the jet struck them. The fragments scattered the superplastic copper stream sideways. Bitumen deformed around the penetration channel, absorbing energy. Wood flour held the matrix together, preventing catastrophic fracture. The turret held. No penetration, no fire, no secondary fragmentation inside the crew compartment. Had 5 men been inside, they would have lived. Subsequent tests confirmed results across multiple angles and ranges. The HCR-2 turret assembly defeated both the Panzerfaust 100 and the 8.8 cm Panzerschreck, the 2 most powerful infantry anti-tank weapons Germany had fielded. Sponson tests showed some penetrations at certain angles. The panels there were thinner and less optimally positioned. More development would have solved these problems. The attachment cables proved vulnerable to high explosive rounds. A near miss could sever cables and drop armor panels. This was a field serviceability issue, not a fundamental flaw. But the fundamental principle was proven beyond any doubt. Plastic armor worked. The scientists also tested HCR-2 against kinetic energy projectiles. The 76 milliton high-velocity armor-piercing round fired by American tank destroyers was used. The plastic provided additional protection against kinetic rounds, though less effectively than equivalent steel. This was acceptable. Against kinetic rounds, steel remained superior. But against shaped charges, the weapons killing American tankers at alarming rates, HCR-2 was revolutionary. Section 7. The Jumbo's Proof. While plastic armor remained experimental, one Sherman variant had proven additional protection could work in combat. The M4A3E2, nicknamed Jumbo by its crews, represented the opposite approach from Flintcoat's exotic materials. Instead of unconventional materials, it used brute force. Massive additional steel plates. Weight be damned. The concept emerged in early 1944 as American commanders anticipated the upcoming invasion of Europe. They knew the Wehrmacht had prepared extensive fortifications along the French coast. They knew heavy tanks and anti-tank guns awaited them. They needed assault tanks that could survive direct hits while breaching German defences. the T-26E1, what would become the M26 Pershing, was under development, but wouldn't be ready in time. So Ordnance Department engineers did what American engineers have always done. They improvised, they modified, they took what they had and made it work. The starting point was the M4A3, the Army's preferred Sherman variant with its reliable Ford GAA V8 engine. Engineers added 38 mm of additional armour plate to the glacis, welded directly over existing armour. This brought total frontal thickness to 101.6 mm. But thickness alone doesn't tell the whole story. The glacis was sloped at 47 degrees. This gave an effective thickness, the amount of steel a projectile must penetrate when striking at an angle, exceeding 180 mm. No German tank gun could penetrate this frontally at normal combat ranges. Not the Tiger's feared 88 mm. Not the Panther's high-velocity 75 mm, not even the 88 mm L71 gun on the King Tiger could guarantee penetration at typical engagement distances. The Jumbo's frontal armour was effectively immune. The turret received even heavier protection. A completely new casting replaced the standard Sherman turret. This new turret featured 152 mm of frontal armour, 6 inches of solid steel. The turret sides and rear received 152 mm protection as well. The gun mantlet, the curved shield around the main gun, added another 177.8 mm of armour. Combined, the turret front presented over 300 mm of protection against direct fire. The standard 75 mm M3 gun was retained rather than the newer 76 mm. This seemed counterintuitive. Why keep the weaker gun on a better protected tank? The answer lay in the Jumbo's intended mission. It was an assault tank, meant to support infantry attacks on fortifications. The 75 mm gun fired a superior high-explosive round. Against bunkers, machine gun nests, and infantry positions, chi was more important than armour penetration. Against German tanks, the Jumbo's role was to survive, not to kill. Let the standard Shermans following behind engage enemy armour. The Jumbo's job was to lead the assault and absorb the first shots. Total weight reached 42 tons, 12 tons heavier than a standard Sherman. Top speed dropped to 22 millitonner, 4 miles per hour slower than standard. The suspension, already strained on standard Shermans, was pushed to its absolute limits. Crews were warned to proceed carefully cross-country. The vertical volet spring suspension was not designed for 42 tons. Extended end connectors called duckbills were added to the tracks, widening them and reducing ground pressure. Without these modifications, the Jumbo would have sunk into soft ground. Only 254 Jumbos were built between May and July 1944. This was a tiny number compared to total Sherman production, but they represented a concentrated capability. They arrived in France in September 1944 as Allied armies pushed out of Normandy. Their impact was immediate and dramatic. Jumbos were assigned to lead tank columns. They advanced first into enemy fire. They absorbed the initial German volleys, shots that would have destroyed standard Shermans and killed their crews. The thick armour deflected 75 mm rounds from Panzerfaust with ease. It resisted 88 mm fire at ranges where standard Shermans would have been annihilated. German gunners reported confusion and growing frustration. Their hits registered. They could see the impacts. Sparks flew, metal rang, but the Sherman kept advancing. It didn't burn, it didn't stop, it kept coming. One Jumbo became legendary. Cobra King, serial number 3283084, led the relief column to Bastogne during the Battle of the Bulge. On December 26, 1944, as the 101st Airborne held their desperate perimeter, Cobra King was the first American tank to break through German lines and enter the surrounded city. Its crew survived multiple engagements that would have killed them in a standard Sherman. The heavy armour that slowed them down also kept them alive. By February 1945, Patton's Third Army was retrofitting jumbos with 76 mm guns in field workshops. The larger T-23 style turret could accept the more powerful gun with minimal modification. The combination of heavy armour and improved firepower created what was effectively an American heavy tank. Of the 254 jumbos built, over 200 survived the war. This survival rate, nearly 80%, was extraordinary for tanks used exclusively in assault roles. Standard Shermans in similar missions suffered far higher losses. The jumbo proved that protection worked. Thick armour saved lives. The question was whether unconventional materials could achieve similar results at lower weight. Section 8. The Mathematics of Death. The statistical record reveals uncomfortable truths. Trevor Dupuy's analysis of US First Army tank losses examined 797 medium and 101 light tanks destroyed between June 1944 and May 1945. For each tank lost, an average of 1 crewman was killed or wounded. Each Sherman carried 5 men. The other 4 survived, but survival often meant severe burns and psychological scars. Infantry anti-tank rockets showed a disturbing pattern. They inflicted 13% of tank losses, but caused 21% of crew casualties. Shape-charge weapons were disproportionately lethal. The jet temperature exceeded 1,000 degrees Celsius. When it penetrated, it sprayed molten metal throughout the crew compartment. Ammunition cooked off. Fuel burned. Crews had seconds to escape. A kinetic round might penetrate and exit cleanly. A shape-charged jet devastated everything in its path. Only 61% of shape-charge hits caused fires, compared to 65% of artillery hits. But rockets killed crews at higher rates. This explained crew desperation for any protection. A few inches of sandbags might not stop a Panzerfaust completely. But if it reduced penetration by even 20%, it might mean the difference between wounded and dead. The psychological mathematics made perfect sense. Any reduction in shape-charge effectiveness translated directly to lives saved. Section 9. From Mockery to Fear. German soldiers initially dismissed American improvised armour with contempt. Reports from Normandy described Wehrmacht troops laughing at sandbag-covered Shermans. "The Americans are afraid," one captured NCO told interrogators. "They know their tanks are coffins." The mockery reflected genuine confidence. German infantry had a weapon that could destroy feared American tanks. The Panzerfaust gave ordinary soldiers power over armour. This was intoxicating for troops who'd watched Allied air power devastate their positions. Finally, they could strike back. By March 1945, the laughter had stopped. The proliferation of up-armoured Shermans changed German tactical calculus. A captured officer described the psychological shift. In Normandy, one man with a Panzerfaust could destroy an American tank. The tanks would burn. We were confident. By February, this was no longer true. The tanks had something on them. We would hit them, and they would not burn. They kept coming. The men began to fear the tanks again. German doctrine had assumed infantry weapons would provide a defensive equalizer. One cheap Panzerfaust could destroy one expensive Sherman. The math favoured defenders. When improvised armour reduced effectiveness, the math changed. Multiple Panzerfausts were needed to guarantee a kill. Multiple shots meant multiple exposures. Multiple exposures meant casualties from tank machine guns. The weapon that was supposed to make every soldier a tank killer had become unreliable. German morale suffered accordingly. Section 10. The Race Against Time. The HCR2 tests proved plastic armour's potential, but the war ended before it reached combat. This was not failure of development. It was triumph of American power. The war ended too quickly. Consider the timeline. Serious shape charge protection development began late 1943. First promising HCR formulations emerged early 1944. Comprehensive testing occurred throughout 1944 and into 1945. First production-ready kit was designed spring 1945. Germany surrendered May 8, 1945. Japan surrendered August 15, 1945. The September tests were intended to validate technology for Operation Downfall. That invasion never occurred. Had the war continued another year, plastic armour would have reached the battlefield. American tanks would have carried HCR2 panels into Japanese fortifications. Thousands of tankers might have survived wounds that would otherwise have killed them. Instead, the technology went into storage. Test results were classified. Flint coat armour kits were never mass-produced. The knowledge became historical curiosity rather than battlefield reality. But the principles did not disappear. They evolved. They improved. They became the foundation of modern composite armour. Section 11. The birth of modern protection. The plastic armour tests of 1945 represented the first systematic American research into defeating shaped charges through material science rather than brute thickness. The insights gained shaped tank design for generations. Every modern main battle tank owes something to those experiments with quartz and asphalt at Aberdeen. Lesson 1. Disruption defeats penetration. A shaped-charged jet maintains its destructive power only while remaining coherent. The copper stream must stay focused, aligned, travelling in a single direction. Any material interaction that causes the jet to diverge, disperse, or fragment reduces its penetration capability. You don't need to stop the jet cold, you need to disrupt it. This was the key insight from HCR2. The quartz gravel didn't resist the jet through strength. It scattered the jet sideways through thousands of particle interactions. Each impact with a gravel particle deflected the jet slightly, multiplied across 10 inches of material. These deflections destroyed the jet's coherence. Modern ceramic armour works on the same principle, but more effectively. Ceramic tiles, typically aluminum oxide, silicon carbide, or boron carbide, shatter when struck by a shaped charged jet. This shattering creates a cloud of ceramic fragments. The fragments interact with the jet, disrupting its coherence and absorbing its energy. The jet wastes its penetration capability, destroying ceramic instead of reaching the steel backing plate. Ceramic is lighter than steel for equivalent protection against shaped charges. This weight savings allows designers to add more protection without making tanks immobile. Lesson 2. Elastomers absorb energy through deformation. The bitumen matrix in HCR2 absorbed energy as it deformed around the penetrating jet. The tar didn't stop the jet directly. It yielded, stretched, and flowed. This deformation absorbed kinetic energy. It also created lateral forces on the jet, further disrupting coherence. This principle reached its apex in NERA, non-explosive reactive armour. NERA sandwiches a layer of rubber or other elastomer between steel plates. When a shaped-charged jet penetrates the outer steel plate, it enters the elastomer. The jet's enormous energy causes the rubber to deform explosively outward. This deformation pushes the inner steel plate away from the outer plate at high speed. The moving plates interact with the jet still passing through. This interaction disrupts the jet, reducing penetration of the inner plate by 50% or more. Chobham armour, developed by Britain in the 1960s and used on both the Challenger and M1 Abrams, employs this principle. Multiple nearer layers are combined with ceramic tiles and steel backing plates. The result is protection that would have seemed magical to 1944 tankers. An M1 Abrams can survive hits from weapons that would penetrate 3 feet of solid steel. Yet the Abrams weighs only 70 tons. Heavy, but not impossibly so. Lesson 3. Weight can be reduced through smart design. Traditional armour philosophy held that more steel meant more protection. The jumbo Sherman embodied this approach and proved that it worked. But the jumbo weighed 42 tons and could barely move cross-country. Its suspension was stressed to the breaking point. Its engine laboured constantly. Its transmission wore out faster than standard Shermans. HCR2 offered equivalent shape charge protection at a fraction of the weight. 10 inches of gravel and asphalt weighed less than 2 inches of steel, yet provided better protection against shaped charges. Modern composite armour takes this principle further. An M1 Abrams provides protection equivalent to over 1,000 millimeters of homogeneous steel against shaped charges. Pure steel armour this thick would weigh hundreds of tons. No engine could move it. No suspension could support it. No bridge could bear it. Smart materials made the modern main battle tank possible. By combining ceramics, elastomers, and steel in carefully designed arrays, engineers achieved protection that brute thickness could never provide. Lesson 4. The arms race never ends. The Panzerfaust led to plastic armour research. Plastic armour principles led to composite armour development. Composite armour led to tandem warhead heat weapons designed to defeat composite armour. Tandem warheads led to explosive reactive armour designed to defeat tandem warheads. ERA led to programmable fusing designed to defeat ERA. And so the cycle continues. Every defence inspires a new attack. Every attack inspires a new defence. The engineers who tested HCR2 at Aberdeen in 1945 started a technological race that continues to this day. In Ukraine, Russian tanks equipped with reactive armour and composite protection burn under Javelin missiles and NLAW rockets. The shape charge principle that made the Panzerfaust lethal in 1944 remains lethal in 2024. The arms race that began at Aberdeen continues on battlefields around the world. Section 12. The Crews Who Never Knew in Summer, 1944. Sergeant Thomas Mitchell of the 3rd Armoured Division wrote home to his wife, "The boys have started piling sandbags on the Shermans. Command says it doesn't help much, but we do it anyway. It's something to do while we wait, something that makes us feel like we have some control. I'd rather die knowing I tried something than die knowing I just sat there." Mitchell was killed 3 weeks later when a Panzerfaust penetrated his tank's side armour. The sandbags had been blown off by the first shot. He never knew that in New Jersey, engineers were developing a coating that might have saved his life. He never knew HCR2 existed. His improvised solution was based on the same intuition guiding Flintcoat engineers. Put something between warhead and armour. Make the jet pass through material that might disrupt it. The intuition was correct. The execution was inadequate. Better materials existed. They just hadn't reached the battlefield in time. Section 13. Production contrasts. The contrast between American and German industrial capacity defined the war. Consider what American factories accomplished. Chrysler Defense Arsenal produced nearly 18,000 Sherman tanks. The factory employed 8,000 workers operating multiple shifts. Fisher Body operated Fisher Tank Arsenal in Grand Blanc, Michigan. Thousands of M4A2s were shipped to the Soviet Union. Lima Locomotive Works converted from railroad engines to tanks. Press Steel Car Company did the same. American Locomotive, Baldwin Locomotive, Federal Machine, manufacturers with no armour experience, learned to build tanks. They succeeded because the Sherman was designed for mass production, standardized components, straightforward assembly. Workers with minimal training could produce quality tanks. This was the Sherman's genius, not armour or armament, but manufacturability. Against this flood, Germany struggled. Each Tiger required 14 days of assembly. Production peaked at 104 monthly in April 1944, barely enough to replace losses. German factories were targeted by Allied bombing. Raw material shortages forced compromises. Late-war German armour showed metallurgical problems. High carbon content made steel brittle and prone to cracking. A Panther built in January 1945 was measurably inferior to one built a year earlier. American armour remained consistent throughout the war. The mathematics of industrial warfare determined the outcome. But mathematics offered no comfort to men burning inside 49,000 Shermans. Section 14. What might have been? Engineers have calculated what might have happened if HCR-2 reached combat. Assume deployment in March 1945. Assume production equipping 2,000 tanks. Assume shaped charge casualties reduced by 60%. In March 1945, shaped charge weapons caused approximately 30% of American tank casualties. A 60% reduction would have dropped total casualties by roughly 18%. More importantly, crew casualties would have dropped disproportionately. An 18% reduction in tank casualties might have saved 270 tanks in the final months. More importantly, it would have saved 400 to 500 tankers from death or serious injury. Each number was a person. Each number was a family that received, or didn't receive, a telegram. Each number was children who grew up with, or without, a father. The HCR-2 tests proved this protection was possible. The war ended before implementation. This is the calculus of military technology. Every month of delay costs lives. Every dollar withheld condemns men to die from preventable causes. Resolution. The M4 Sherman's legacy remains contested 8 decades after the war ended. Critics call it a death trap, pointing to the burning hulls that littered every battlefield from North Africa to Germany. Defenders note its reliability, maintainability, and overwhelming numbers. Both perspectives contain truth, but the story of improvised and experimental armour reveals something deeper about the American way of war. American tankers faced terrifying reality in 1944 and 1945. Their vehicles could not survive hits from common German weapons. Their government had prioritized quantity over quality. Their commanders had underestimated the threat posed by new German anti-tank weapons. They were dying in vehicles that their own officers privately acknowledged were inferior to German armour. The official line was that the Sherman was adequate. The men inside them knew better. They responded with characteristic American ingenuity. Sandbags and track links, concrete and steel plates salvaged from wrecks, anything at all that might give them a chance to survive. Their improvisations were often ineffective. Sandbags provided minimal protection and added crushing weight. Track links might have made penetration worse by normalizing incoming rounds. Concrete cracked and created dangerous spalling. But the crews kept trying. They kept improvising. They refused to simply accept death. American engineers took that desperate creativity and transformed it into systematic science. They tested materials no one had considered for armour. They measured performance against shaped charge weapons. They discovered that unconventional materials could achieve what conventional steel armour could not. HCR-2 worked. Quartz gravel and asphalt, road construction materials, defeated the weapon that was killing American tankers. The jet that punched through inches of hardened steel dissipated harmlessly in tar and stone. The war ended before these discoveries reached combat. Germany surrendered in May. Japan surrendered in August. The Aberdeen tests in September were too late. But the knowledge didn't disappear. It evolved. It improved. It became the composite armour protecting tank crews today. In fall 1945, at Aberdeen Proving Ground, a strange-looking Sherman survived a Panzerfaust hit. The quartz and asphalt held. The superplastic jet that had killed thousands of Allied tankers dispersed harmlessly. The hull remained intact. The crew compartment, empty for the test, showed no penetration. Had 5 men been inside, they would have lived. Total Sherman production during World War II, 49,324 tanks. Total Tiger, the Fund production, 1,347 tanks. Total Tiger II production, 492 tanks. The mathematics of industrial warfare favoured America overwhelmingly. But mathematics offered no comfort to the 5 men inside a burning Sherman. For them, survival was binary. Either the armour held or it didn't. Either they lived or they died. There was no averaging. No statistical analysis, just fire or survival. The plastic armour tests proved the armour could hold, not through brute thickness, not through impossible weight, but through scientific understanding of how shaped charges worked, and how they could be defeated. Dr. William Gruber retired from Aberdeen Proving Ground in 1962. He rarely mentioned the tar-covered Sherman that survived a Panzerfaust on a September afternoon in 1945. Perhaps he didn't think it was historically significant. Perhaps he knew it would be decades before anyone understood what that test meant. But that test mattered. Those 10 inches of quartz and asphalt mattered. They proved that shaped charges could be defeated without adding impossible weight. They proved that material science could solve problems brute force could not. They proved that tankers didn't have to die in coffins. Every Abrams tank serving today carries descendants of that strange coating. Every Leopard, every Challenger, every modern main battle tank incorporates principles first validated in those Aberdeen tests. Ceramic armour, elastomer sandwiches, composite arrays designed to disrupt rather than simply resist, all trace their lineage to HCR2. The men who died in burning Shermans in 1944 and 1945 never benefited from the knowledge gained from their sacrifice. They never knew their deaths drove the research. They never knew their desperation inspired the improvisations that led to systematic study. They never knew their burning hulls proved that something had to change. But something did change. In September 1945, a Panzerfaust failed to penetrate a Sherman tank. The strange armour that looked like road tar worked. The crew inside, had there been one, would have survived. They laughed at the rubber armour. They stopped laughing when it worked. The quartz and asphalt that everyone mocked had done what steel plates and sandbags could not. It had stopped the shaped-charged jet. It had protected the crew inside. It had proven that unconventional thinking could solve problems that brute force could not. The future of tank protection had arrived, wrapped in tar and gravel.